Yeah, and then I would like to introduce the first speaker, Professor Maren Bennewitz. Maybe you can set up your laptop while I introduce you. So, Maren is a professor for computer science here at the University of Bonn and head of the Humanoid Robots Lab. She has published over 120 peer-reviewed papers and regularly serves as editor. She's been a principal investigator in several national and European projects and is on the board of the Cluster of Excellence PhenoRob, which is about robotics and phenotyping for sustainable crop production. Her research focuses on robots acting in human environments, and today she's going to talk to us about
I adapted the title.
About foresighted robot behavior incorporating human preferences.
Exactly. Thanks a lot for the kind introduction, and of course, thanks a lot for the invitation. I'm really happy to be here and part of this exciting initiative. So I adapted the title of my presentation to the title of the event today, and actually it fits well to the content I'm going to present. Sorry for that I confused you. So I'm head of the Humanoid Robots Lab at the Computer Science Institute, and in our research we apply AI and machine learning techniques to mobile robots. So we develop techniques for robot navigation, for object manipulation, for active perception, and for human-robot interaction. And in the remainder of my presentation I will just present some example projects, so give a rough overview about the research we are doing. So, service robots acting in human environments should avoid interferences with the users and act foresightedly. So the robots should adapt their behavior to the users and not vice versa. And here are 3 examples for undesired robot behavior. So in this situation, the robot and the human are somehow stuck, so the robot is blocking the way of the user. Here, the robot follows too closely the user, which might be annoying. And in this situation, the robot is too far away, so no fast reaction of the robot would be possible in case service would be needed fast. And of course, all these situations should be avoided by the robot, so it should act foresightedly. So this is the motivation about the research I'm going to present soon. And furthermore, actually this image reminds me of the cover image you were just showing, right, with the obstacles in the way. So robots should not just treat objects as static obstacles, but should distinguish between different types of obstacles and reason about possible actions to overcome them. So it's the same motivation, I would say, for tonight. So for example, in this situation, like the blocks could be stepped over by the robots, the balls could be kicked away, and the robot could step onto the boxes or move away the stuffed toys in order to free its path. And in the following, I will present solutions to these 2 problems: foresighted navigation, taking into account user-preferred robot behavior, and motion planning and navigation through cluttered regions. So I will present the solutions we developed for these 2 problems. So first, imagine a service robot acting personally for you at home. We have individual preferences on how the robot should interact with us, how the robot should traverse the home, how it should approach us in the vicinity. So we have personal preferences on how close the robot should come, how fast it should drive, should it pass before or behind us. And we developed a virtual reality interface to teach a robot the desired navigation behavior. And this is shown on the next slide. So to demonstrate preferred navigation behavior, the user draws trajectories onto the ground in virtual reality with a handheld controller, which emits a beam. And the trigger on the backside of the controller also allows the user to select different robot speed profiles. I apologize that man is displayed here. So the user displays different robot trajectories, and the robot directly executes those trajectories in virtual reality, and the user can then decide either to redraw the trajectory if it does not reflect the navigation preferences, or to take or to agree to the trajectory. And in case the user agrees to the trajectory is taken for learning the preferred navigation behavior later on in the session. So we collect different types of such trajectories for each individual user and learn a user-specified navigation behavior for the robot. We performed the user study in our lab. So the ultimate goal is to show that using our virtual reality interface, we can generate improved human-robot navigation experiences. So we invited like 24 participants into our lab. We gave them a tutorial onto the virtual reality interface. Then the users demonstrated their preferred navigation behavior to the robot in virtual reality. Then the first session was over. We trained individual controllers for the users that participated in the study. And in the second session, we evaluated first the learned controllers for each individual user in virtual reality, and later on also on the real robot. So the users evaluated the learned navigation behavior of the robot. The results of the user study we performed were as follows. So the users rated the virtual reality interface as very intuitive and comfortable to teach the desired trajectories and the robot speed. And also regarding the navigation experience, they told us that their personal preferences were mostly reflected, and this resulted in more comfortable robot navigation behavior in contrast to standard approaches that were applied to mobile robot navigation. So we showed that really using our virtual reality interface, this was intuitively to use for like naive users that didn't have any experience with robots to teach the robot their personalized navigation behavior. So, coming to the second topic, navigation through cluttered regions. So as I said, a robot should reason about possible obstacles to overcome objects blocking their way. And here we exploit knowledge about different obstacle classes to choose the appropriate robot actions. And in this video, I show the learned behavior for our robot. So here on top, you see one of our robots. The robot has a RGBD camera on top of its head, with which it perceives the obstacles in the environment. And down here, you see a map of the static obstacles in the environment, basically the walls and these cupboards here. And when the robot starts to move, it will detect the obstacles blocking in its way. It cannot see this obstacle at the initial position because the RGBD cameras have a certain range in which they measure the obstacles. But as soon as the robot moves and comes closer to the obstacles, to the objects, it will perceive these objects here, and they will be inserted into the internal map of the robot, as you will see soon here. And the robot then chooses the action to step over those blocks here initially, but when the amount of blocks actually that the robot detects increases, the robot decides that it is faster to move away the stuffed toy. So the robot moves close to the stuffed toy, grabs it, and puts it out of its way. So now the way of the robot is free. Its internal map representation has also been updated, and the robot is able to reach its target location, which is somewhere down here. Here's another situation where these two objects are blocking the way of the robot, and in this situation the robot will just kick away the ball to free its path. Okay. So now I want to say some words regarding our cluster of excellence PhenoRob. So PhenoRob is short for Robotics and Phenotyping for Sustainable Crop Production. And our mission is to develop new technologies for sustainable crop production with reduced environmental impacts and increased yield. So contributions from the robotics side are here. We want to develop intelligent agricultural robots. We want to realize high-precision plant-specific interventions, and we want to perform continuous monitoring of the crops, fields, and environments. And one part of this project is to realize autonomous harvesting with robots. And here, the perception and monitoring of the fruits is, of course, key to yield estimation and realize autonomous harvesting. But the challenge here is that the fruits, for example, sweet pepper fruits, are typically occluded by leaves or peduncles of the crops, and we must plan appropriate camera poses in order to detect the crops and cover them from different situations. And we contribute here viewpoint planning techniques and position and volume estimation techniques to estimate the fruits and monitor the growth of on the crops. And here are the individual steps that are necessary to realize autonomous harvesting. So first, in the current camera image of the robot, we have to detect like sweet pepper fruits here. So we apply here techniques from computer vision. Then we need to learn an individual internal representation for the robot, which the robot can use to reason about actions to execute and also to perform viewpoint planning, so which regions have not been covered yet by its sensors. So using this map representation, the robot performs also view planning, so to decide which next camera view should be acquired to get new information about the crops and the sweet peppers. Then we perform shape estimation because, as I said, the sweet peppers typically cannot be covered from all possible directions. So we need to perform like a shape completion method in order to estimate the size and the exact position of the fruits. And finally, we can then realize harvesting, so the robot can grasp the fruits and cut them off. And I show you some recent videos we recorded in the glasshouse. So here you see this is a 3-arm system, one harvesting robot. The robot has on one arm the camera to observe the fruit, and the other arms are used for the manipulation action, to grasp the fruit and then cut it off. On top there you see the current camera view of the robot, of this camera here, and this is the internal model the robot learns during operation. I start the video. You see how the model evolves, how the fruits are detected, and soon you will see how partially detected fruits are completed, so the shapes will be completed. Here now we will complete those shapes so that the robot knows about the volume of the fruits and can then finally grasp a fruit. This is our most recent video from the glasshouse. Also here the robot performs the same modeling and shape estimation, then grasps the fruit and cuts it off and collects it. So this was my short introduction to our research topics. So what are the take-home message? Robotics is a physical embodiment of artificial intelligence in the real world. So we typically apply several AI methods and machine learning methods to realize intelligent robot behavior. I think I could convince you that AI and robotics are really an exciting research area. And of course, AI and robotics contribute to sustainability. Thank you.
Yeah, thank you, Maren.
Thank you.